I have the great pleasure of hosting Professor Bjarne Stroustrup. So, Professor Stroustrup, thank you so much for your time and for doing this podcast.
Okay, thank you. Thanks for inviting me.
Wonderful. So, I'd like to start our discussion with the first question. So, basically, what inspired you to create C++, and what were some of the biggest challenges you faced during its early development?
I came to Bell Labs back in 1979, just after my PhD. And my PhD was in distributed systems, so obviously I wanted to build a distributed system. And I walked around Bell Labs and I looked at the doors with the names on them, and it was intimidating. These were sort of the heroes of the time. Uh, Brian Kernighan and Dennis Ritchie for C, Alejo for compilers, and just went on and on and on. And I realized I'd better do something good, otherwise I didn't belong here. And so I decided I was going to build, after a while, I decided I was going to build a distributed Unix. So if I had managed to do that, we would have gotten the first Unix cluster maybe 10 years early. But looking at what I had and what I could do, I realized that I didn't have a programming language that was good enough for it. I didn't have the tools. The way I was thinking about it was I didn't have the tools to build such a system. In Cambridge, where I got my PhD, I had first started building a simulation of a distributed system in Simula, which is an excellent language for that kind of stuff. The only problem was that I was bringing the departmental computer to its knees, and grad students don't get away to do that. It's the performance just wasn't there. I could stop a mainframe all by myself. So I had to move to another computer where the support was so poor that the astrophysicists and the chemists couldn't use it. And so I could get it to myself and I'd get some work done. But there was no Simula there, so I had to write in BCPL, which is very low level and very fast. And so I learned a couple of things from that. One, that I want the support of a high level language. I want static type safety. I want the ability to build my own types, things like that. I want coroutines. And then I also, on the other hand, want from the low level thing, I want to be able to manipulate hardware. I want performance and, want to be able to do things that the language designers hadn't thought of. And I was very convinced when I left Cambridge I would never attack a problem again with inferior tools. And so when I started thinking about building a distributed operating system based on Unix, I realized I was just about to make that mistake again. And I needed something for the low level stuff. I had to write memory managers, thread implementing a thread process system. I needed device drivers. I needed communication channels. That's all kinds of fairly low level stuff that manipulate hardware and devices and such. And in the context of Bell Labs, C was the obvious choice there. I also needed some high level stuff. I needed to be able to say, this is a module and this is another module, and they are separate and they talk in this particular way with this particular protocol and things like that. And since I was thinking of distributed systems, I couldn't assume shared memory. So a lot of it was thinking along the lines of message passing and that kind of stuff. For that, I needed a high-level language, and Simula was pretty ideal for that, except that it was very much too slow, like 50 times too slow was my guesstimate at the time. And so I needed to merge the facilities I liked from C with the facilities I liked from Simula, and so I did. Fortunately, nobody told me it was impossible. But hey, you're just graduated, so you don't need know that things are impossible. And I put low-level facilities into Simula, but their compilers were very large, proprietary, and only ran on some hardware, whereas C was cheap, easy to hack if I needed to, and ran everywhere. And I had superb local support. I mean, it was invented on the same corridor I was having my office on. So I decided to put the similar facilities into C. And well, I guess the rest is history. It worked, and you can now use classes, you can build your own types and design systems that can actually you can afford to run. Because one way of saying what I learned was that you don't just have to have a facility, you have to be able to afford to use the facility. Otherwise, people will do some lower level stuff. And that has been a rule of thumb for me ever since. And I usually don't have the most advanced computers available. Certainly, a new researcher wouldn't have it. The grad students didn't have it. So I better design things to run on an average computer or even a cheap computer. And so these days, you find C++ in the strangest places. I was talking to a guy last year who used it to program power supplies. You know, these little things that sit between your laptop and the wall.
Yeah, right.
You can run C++ in that. He was
Oh, really?
doing it. Yeah.
Mm-hmm. I see.
It's so it goes from sort of advanced stuff, big stuff, to things that are basically, I mean, the processor is sort of like that. Um, so it sort of met my criteria.
I see. And what would you say is the best way to add new features without making the language too complex? And also, the following question would be: what are some features of C++ that you are most proud of? And are there any features you wish you had not included in C++?
Oh dear, that's at least three questions, but I will try. Um, First of all, um, every couple of weeks, somebody comes and tells me something. They tell me C++ is too complicated. You really have to simplify it. Yeah, I agree. It's complicated. Yes. And by the way, there's these two features I need yesterday. You must put in these two extra features. I badly need them. Yes, this is difficult to do both. And by the way, I have a million lines of code. Don't break it.
Yeah.
This you could call a trilemma if you didn't mind doing violence to the English language, and it's impossible. But so I come to the conclusion that I can't actually break the language because it's not just a million lines of code; it's a few billion lines of code I would break, and I would annoy a lot of people. Uh, but I can change the way the language is used. So there's two things we need to do to move forward. One is to provide better solutions to the problems people have. In other words, we have to see what people are doing with C++, we have to see what the problems are, and we have to solve the problems. This is just basic engineering. You look for feedback and respond to it. But you can't break the old stuff. So sometimes you add a new feature, sometimes you modify a feature in a compatible way, sometimes you add a library. Um, and now you get obviously a bigger language than you had before, so more people will complain about the complexity. but you don't have to use the old stuff. You don't have to write code the way we did in the 80s. As a matter of fact, it's a very stupid thing to do mostly, and I certainly don't do it. So you try and design a set of guidelines for how to use C++. And partly that's what you do when you write papers and books and such. And partly you actually write specific guidelines that says if you do this, you're staying in modern contemporary C++ and don't go into those dark corners over there. That's where the trouble are. But we can't get rid of those dark corners for two reasons. One, it's all the code that exists. And two, you need some of those low level, dangerous, hard to use features to implement the higher level features. A classical example is that a lot of the problems with C++ comes with pointers and arrays and uninitialized uh, uninitialized objects. On the other hand, to build a vector that doesn't have those problems, you need the pointers and arrays that that you don't really want everybody to use all the time. So you build a set of guidelines. You try and talk people into writing modern code. You try to convince people that it actually is at least as fast or faster than sort of traditional C code, and that it's not bigger and it's as portable, all of these good things. And then currently there's a lot of talk about safety and security, and we want to enforce those guidelines. We've been trying to do that for years. The guidelines I've been working on is called the C++ Core Guidelines, which is done by a group of people who've been doing it for years. And some of those rules are actually, you have tools for guaranteeing it. Microsoft Visual Studio's Static Analyzer, Clang Tidy, and a little bit in GCC. And I want more of that. That's one of the things I'm working on now.
And what role do imagination and creativity play in creating something as structured as programming language? And also, do you see that as an art or science or something else?
I'm pretty sure it's an art and a science. That is, there's definitely scope for creativity. People who aren't creative build something that's just like the other one, and you will never actually make progress. You get a lot of mediocre stuff that works for a lot of people, but you don't get progress. On the other hand, if you don't have science, if you don't have theory, you don't know how to build it right. You cannot prove that things work. You do not know where the limits are, what can be done, what cannot be done. There are people who demand things of you that just are impossible. I was talking to somebody a few years ago, and they demanded that transactions should take place with exactly the same effect in Sydney and Tokyo. And they also wanted them fast. They had to be as fast as anything everywhere. And I scratched my head a little bit and says, "Well, you'll have to take this up with Dr. Einstein because we have a slight problem here that has nothing to do with computing. I can give you exactly the same answers, but it'll be slow. I can give it fast, but then you are going to get slightly different answers. We have transmission delay, and also there are, I think, more computer sciencey. People want uh, guarantees that there's no resource leaks, and they also want to use C pointers to hold resources. But the point is that I can easily write a program so that you're up against the hoarding problem. It is actually impossible I can write programs that makes it impossible to prove correctness. That's not difficult. Everybody knows that. But that was just two kinds of science that you really have to appreciate and respect. And theory, in my opinion, is not a great guide to what you want to do, but it's a great help for once you have decided what to do. Then you have to know your theory to build it properly.
I see. And do you believe that the essence of programming can be fully captured in a single language? Is there a perfect programming language, actually?
Well, certainly there isn't one. I guess the question is, can there be one? And um, you would sort of like there to be one, but then you will find that it has different aspects. The guarantees you want for bit fiddling hardware interfaces with timing constraints and really bit fiddling are not actually compatible with a high level view of uh, type safety and resource safety. So if it was a single language, it would have high level and low level features, which, by the way, is how I've been working with C++ roughly forever. It's a different same aspect of that. So basically, in theory, we would like such a language, but I don't think it can exist. And if it is, it will be too big and complicated. And so this is why we've got a lot of programming languages. I see a lot of sort of mixed C++ and Python. Gilder van Rossum wanted a language that was usable by everybody, and I wanted a language that was basically good for engineers. I don't want everybody to program the brakes in my car or the navigation system in my plane, if I had a plane and if I had a car. But you see what I mean. Different needs are served by different languages, and different people has different constraints. So the average person writing a website for a small company is a very different person with a very different set of concerns than an engineer that is controlling uh, the, the brakes of a car or the motor that, in an electric car, something like that. So I suspect that the difference between the different domains and the different needs will lead to different languages, at least in the next many years.
Hmm. And do you think the programming is basically fundamentally about solving problems or expressing ideas?
I don't know what the difference is.
You need to express some idea in order to be able to solve some problem.
Exactly. That is, I think you should always start with a problem. That is, when you get an idea, it's usually because you think you can do something better than it's done now, or something isn't done now, and I would like to do it. And so the problem drives the idea. And the programming language is the language for expressing solutions, expressing ideas. A language in itself isn't a solution. It's a language, and people sometimes get confused there. I mean, there's a lot of difference between understanding basic English and writing a play by Shakespeare. There is much more to it than the language and the grammar and the vocabulary. There is how to express a notion, how to structure a solution or a play or something like that. So you have the language, it gives you the grammar, it gives you the vocabulary, and then you can write the story or the solution to the problem. And in both cases, you sort of build things, build concepts, you build uh, ideas out there. And so a lot of C++ is there to allow you to express more advanced ideas as you go along. Build your own types, build your own collection of types that interact with each other, express constraints on types, on things like that.
I see. And how do you see C++ fitting in with other modern programming languages such as Rust, Go, or Python?
Well, C++ is a very modern language. It has pioneered a lot of things. I remember when people complained bitterly about class hierarchies. I remember people complaining bitterly about operator overloading. I remember people screaming about generic programming, how horrible it was, especially from the Java and C Sharp groups, till they adopted it. And by the way, you can't have generic programming without overloading, because the point is that uh, you you have code that works the same for different types. And these days we have zero overhead, uh, fully constrained templates, much better generic programming than I think you can do in any other language, at least not under cost constraints. You can do almost as much in statically that you could do dynamically in another language. I was looking at some student projects this last couple of days, because it's the final project time at Columbia, and quite a few were mixing Python and C++, which makes perfect sense. But interestingly enough, a lot of their code were line for line equivalent. That is, the main difference was that the C++ does the checking at compile time. So you don't have to write the error handlers, and it runs faster. So that was sort of nice.
And what would you say are the features of C++ that are underutilized by developers?
Um, the C++ community is very large, uh, 6, 7 million developers. We don't quite know how to count programmers, but that in that ballpark. And different sub-communities use the language to a different extent with different purposes. I think the most fundamental thing to understand about C++ is simply the use of constructor-destructor pairs for managing um, for managing resources. And a resource is anything, not just memory. Memory locks, I've seen done for shaders in graphics. Basically, you have a scope in which an object is live, and you control the whole lifetime of the object. You can move an object from one scope to another, and you can construct it, destruct it, and that's really fundamental. And where that doesn't work is if you litter your program with a lot of pointers in an undisciplined manner. I'm not against pointers, but I'm against using them as if they were a high-level feature. And so you start out with constructors, destructors, and they were in C++ from roughly day one, or at least the first week. Because I was coming out of an operating system world, and I knew that resources was essential. And if you do embedded systems, resources are essential. If you leak, sooner or later you crash. And we have C++ on Mars and such. You can't send a repairman if you crash because of a resource leak. It doesn't work. And so that's where it all starts, and a lot of it comes from there. So to represent resources, you need classes. You need to build up your own types that manages the resources they need to function. And actually, the first one that came in before it was even called C++ was coroutines. I built some coroutine classes so that I could write concurrent stuff. And the whole standard library is based on mostly classes. And then the minute you have classes, you realize that you need to parameterize them. Maybe the physicists can do with just vectors of double precision floating point numbers, but actually that's not even true anymore. They have vectors of other things. But anyway, if I want to write a chess application, I want a chessboard. I want a two-dimensional vector of chess pieces. So I need to have my containers of stuff, and then I need to parameterize them with what's in them, and maybe how to get data and whether logging is necessary. There's a fair amount of parameterization needed. And once you build those types, you find you want to use them, and you want to write algorithms that use those types. And if the types are parameterized, well, then um, the algorithms must be parameterized too. So if I want to sort something, in modern concurrent in current C++, I just say sort x, where x is a container, and the type system checks that x has the properties needed for a sort. And you can look up in the standard what that is. It means that x has to have a random access sequence of elements, and those elements has to be compared with the less than operator. And we can check that at compile times. We do. It's called concepts. It's relatively new, but it's. I mean, I've been thinking about it together with friends for at least 15 years, almost 20 years, and we finally got the solution that was flexible enough for C++. And so you sort of build it up like that.
And would you say that the C++ is the most powerful programming language ever built?
Most powerful is an ill-defined term. Most powerful at what? I would say that for sort of engineering applications where you need to use hardware very well and it's complicated enough that you manage complexity, yes, there it is. But you could also define most powerful as allowing most people to write simple code, and that obviously is not C++.
Mhm. And how has your view on object-oriented programming evolved over the years?
Um, Not as much as you might think. Um, what I wanted classes for was primarily to get my own types, vectors, function objects. After a couple of years, I realized I wanted objects that behaved like functions, so that they could have a state that was maintained between calls and uses. Coroutines is a simple example of that, but there's a lot of these function objects. They turn later into lambdas because they do exactly what lambdas does in other languages, just in a slightly different way. And so I wanted objects. Hierarchies came slightly later and was not quite as used by me as it was by some people, and it certainly wasn't everything. There were people back in the 90s that claims that everything should be an object, that every object should be part of a class hierarchy, and every operation should be an operation on an object, a member, a method, and it had to be virtual so that you could override it. In my opinion, that easily gives systems that are too interconnected and uh, too slow and too hard to understand because everything can be overwritten at any time. Very flexible, very powerful, but not really what I wanted. An example at that time was I said, if this program runs in a in a minor telephone switch in Bogota, and the problem emerges on a rainy Sunday night, there will not be a programmer in the house. You cannot just say, well, when there's a problem, drop into the debugger. You actually have to write programs that will survive. And maybe if everything is screwed up, you can reinitialize the whole system before, but you can't just die. Furthermore, you have to make sure that you have to minimize the number of error handlers. So the type system helps you a lot because there's things that you can't do if you use the type system well. And that's one of the reasons I want higher level code, because then the errors are handled before, are detected before you ship. That's the idea.
Do you have any favorite personal project or application that is using C++?
Um, it's embarrassing, but just now I don't. Um, I'm working on the C++ standard. That takes an amount of work, and I am teaching. That takes some work. I've had some little projects for to do with the teaching, uh, but really sort of a major project I haven't had since I left Morgan Stanley, where I was working before. And so most of what I'm doing has to do with either the standard or the teaching, and that I would call small experiments as opposed to a major project. I mean, I do write code every week, not most days, because otherwise I couldn't do what I'm doing, but not a major project just now.
I see. And who were some of the most influential people in your career?
Um, I would say probably Christian Nygaard, who was the one that invented object-oriented programming and Simula. I met him when I was a grad student in Aarhus. He was a visiting professor, and I spent a lot of time talking with him, and for years after I had graduated. Learned a lot about how to structure systems and how to think about software from him. Another person would be Brian Kernighan. Um, when I went to Bell Labs, obviously I had to learn C, and he wrote the book on it. Dennis Ritchie wrote the manual, and all the tutorial stuff was from Brian. So I learned a lot about design and of expressing design, how to write a technical piece of writing. I learned a lot from him. This idea of you have some code, and then you have some discussion of principles, and then you have some more code, discussion of principles and techniques. Never have a whole bunch of code there and then explain it somewhere else. And never ever just give people the code and let them guess what it's supposed to do and why. And never just give people the theory, the principles, because they can't make a concrete example. This intertwining of principles, techniques, and concrete examples, I think I learned mostly from Brian. And there was Doc McElroy at Bell Labs, who was the guy that we all went to when things were difficult. And he was very good at understanding things. So you spend half an hour explaining what your problem is, and he feeds it back to you in 3 minutes. He was really smart. Uh, and it was a very good environment for working, very collegial. You could always go and find an expert for something. This is the best place on earth at the time, and you could really go into a senior person's office and discuss things with them, even as a young researcher. And great great people there.
Right. And what lessons have you learned from maintaining a language over several decades?
Um, oh dear. Uh, I think I do not know how to really do it. Governance is important, and I didn't realize that from the beginning, and I'm not good at it. That is, you need somebody to manage it. So my idea today, as it was in past, would be to have a small group, a secretariat that has executive powers, decide what goes in, what goes out, and a large community that uh, come up with ideas and suggestions. And this is not the way C++ works. We have more than 200 people are turning up at the meetings, and maybe close to 500 people reading the papers and writing papers. It is really, really hard to maintain coherence and direction. And so I guess the answer to your question is work very, very hard and provide coherence and direction. Decide what's important and what isn't. There's a lot of people who think that the right solution is always the one that can do everything for everybody. And that, in my opinion, is hardly ever the case. Because if it does everything for everybody, then it is too big and it probably isn't specialized enough to help the people that really need some of the hard things. So for C++, I talk about the onion principle. The idea is that you build the ideal interface. It has enough information there to check that the calls are correct, either at runtime or at compile time, but it may not do everything. Like the sort I mentioned before could sort something provided it had a less than operator. So we add another parameter so that's defaulted to less than. And then if you want to give it a sorting criteria, maybe greater than or something else, then you can just add it. The interface is there, it's sufficient, and it doesn't get in the way of zero overhead. Now, so once you have that interface, quite often you find that there's some things you can't do. So you have to peel off a layer, and you can then do more, and you peel off another layer, and you can do more, and you get down to the hardware, and you even peel off that and get specialized hardware, and you get all the way down to the FPGAs. And the reason I call that the onion principle is that each time you peel off a layer, you have to write more code, you have more opportunities for making mistakes. In other words, you cry more. So that's why it's the onion.
And if you could start over, would you do anything differently with C++?
Obviously, I think the major things were right, but that every detail can be improved in retrospect. We could get a better syntax, we could get simpler solutions for things, and that's the way I look at it. It is not the perfect language for everybody. No language is, in my opinion. If anybody claims to have a perfect language for everybody, it's either a salesman or a fool, and probably both. Um, let's see. There's something I should say. Um, yeah, as an example of the evolution that we talked about in the beginning, we have to make sure we get. I didn't emphasize it, but when you design something, you have to know that it's not the final uh, release. You have to make sure that you don't get in the way of uh, future needs. And so you try and get things as right as you can and then not close the door for the future. And one example of this was back in the 1880s, late 1880s, I realized that macros would not, they're not sufficient for generic programming. It works very well with sort of two friends, but anything larger, it's a mess. So I designed support for generic programming, what's now called templates, and I realized almost immediately there was three things I wanted. I wanted full generality, or as I was saying at the time, I don't want a language that can only do what I can imagine. Two, I want it to run as fast as C, equivalent C, the zero overhead principle. You really if people can't, if it doesn't run fast enough, people will write in the lower level facilities. And then finally, of course, I wanted decent interfaces, as I was just talking about them before, with enough information for checking and all of that. And I mean, I was the one who put function argument typing into C, so this is not new. Um, and I realized very quickly that I couldn't get all three. I could get performance, I could get generality, but designing interfaces that supported that was beyond me. I actually literally traveled the world talking to people who thought they knew generic programming and usually did better than me, and nobody could do it. The point is that if you put in an indirection somewhere, you start running really slow. So you can't do that. That means that the classical implementation of abstract data types is simply not allowed. And so I decided I had to make do with two out of three, performance and generality. I mean, this is C++. I didn't have any choice, I felt. And then somewhere in the mid noughts in 2007 or something like that, I started working on the notion of concepts that my friend Alex Stefanov had been working on and thought out. First, I thought I didn't need language facilities for it, but I realized I had. I should, by the way, have mentioned Alex Stefanov as an influential person in specifically in the area of generic programming. But anyway, I figured out how to do it, and then, of course, the standards committee was quite reluctant. There was lots of people who were experts in the rather horrid workarounds that you needed if you didn't have concepts. And but it's in now. You can do proper type checking of calls to generic functions, and you can get the error messages right at the point of call. And it doesn't cost anything. It's all in the compiler. And actually, for a variety of reasons, it actually runs at least as fast, sometimes faster than if you didn't have that type checking. Because
Right. And what keeps you motivated after all these years in the field?
applications, there's some really cool applications of C++. It's all over the place. I mean, some things are like that power uh, power supply. I mean, what? And then you can see the big Google server farms. I mean, the Mars copter is really cool. And I was talking to the people at CERN, and they found Higgs boson. It's fantastic. You go to. I'm not sure. I like. I mean, I'm not a games person, and I'm not. I don't watch superhero movies and things like that. But it's C++. Uh, the graphics and the animation there, it's amazing.
And what resources do you consider essential for mastering C++?
I don't know, a small laptop.
I mean, some books, some lectures.
I know. So one thing that people don't get, sometimes even professors don't get, is that not everybody is at the same level. So you see on Amazon people criticizing a book for being advanced. It's not for beginners. It's bad. Wait a minute. Not all readers are beginners. And so, what I have done was initially I had to explain all of C++, and you get these thick books. But lately, I have focused on two things. How do you teach real beginners? How do you teach programming? So I have a book called Programming, um, Principles and Practice Using C++. It's really important it comes in that order. It is not a C++ textbook, even though it's also that. but it's focused on something else. This is very much the view that a language is a way of expressing ideas, and if you don't have any ideas, you're lost. So it tries to teach you how to use the language to express useful things. And the other book, which seems to be more popular, it's called The Tour of C++. It's now the third edition. Actually, so is my textbook, and that is aimed at people who knows how to program. People who very often know either C or C++ as it were 10 years ago. How do you want to get up to speed? And it's the the text on programming language features and such is 250 pages. It's something a good programmer can read over a weekend, and that's important. So I aim at those two things. And when programmers come up and says to me, "I want to know all of C++," my answer is, "Why?" I mean, if you keep all of that in your head at all times, you won't get any work done. What you do is you decide what it is you want to do, and then you look up to see what C++ has to help you. Um, yes.
Yeah, and how do you feel about the role
Wait,
of C++?
wait, wait. Yeah, I only answered half of your question. You need a good implementation. I mean, you can do things like Compiler Explorer, where you can sit and do it right from your browser, which is really good for small experiments. And then I think you need a good programming environment. And a good programming environment varies from person to person. Uh, these days, I either work from the command line. I was brought up that way, right? Or I use something like Visual Studio, which has really good support for C++. And currently, the Microsoft compiler is more up to date than the other major compilers. But that changes every couple of years. One of the compilers get better, and then the others have to catch up. That's the advantage of not having a monoculture. You actually have competing implementations, competing IDEs, competing build systems. It's very confusing for beginners. There's not just one answer to every question, but it's healthy.
Right. And how do you feel about the role of C++ in education today? And what advice would you give to educators teaching C++ in 2025?
Um, it's a bit hard. Um, Again, there's many different uh, levels, many different needs. I think there's some fundamentals that everybody should learn, and C++ is good at that. A lot of times they do the, I think, daft way of teaching C first. That way people can learn all the bad habits and get all of the problems before they get the solutions. I don't think that's good. I think if you're going that way, which might be a sensible thing if you're teaching engineers and people who deal with hardware and such, then go for C++ first. That's what that programming book I wrote was written for when I was teaching at Texas A&M, and I had a large group of undergrads that needed to be taught. So it works. I hear people saying you can't teach C++ as a first language. Well, you can. I've done it for tens of thousands of people. It works. It's just not every programmer, every person who should write programs should write C++. I mean, there are languages that are meant to be easier for people who aren't engineers, people that doesn't have a, um, a university education and such. So maybe use some other language. But if your aim is to write the hardest, most difficult systems under the most constraints, C++ is a good language, and it has the fundamental principles that actually make sense and add up. And if you focus on those rather than on the obscure corners, then you can do much better. So I mentioned the C++ core guidelines. Uh, my books follow that. I don't particularly emphasize it, but I'm teaching some of the low-level stuff only when it's labeled as low-level stuff. Go there only if you want to implement something that needs it. It's taught as a strongly typed high-level language, and that's how I think it should be taught. And you can do all the things with it and use all the libraries and things like that.
What do you think of the increasing use of frameworks and libraries over core language features?
Um, for most applications, having the right library is the right thing. It's good. Writing in bare language is unpleasant and not very productive and somewhat error prone. So you always use libraries. So even in the most minimal program, you use parts of the standard library. So for instance, I think something like day 2 of teaching freshmen, I use strings and vectors. I don't want people to fiddle around with C-style strings and arrays. It's just getting them into trouble. I think pointers are introduced in chapter 17. You can get a long way, but you need libraries. Definitely, you need libraries. Now, people love frameworks, but quite often it is de-skilling people who are using them. And you can only do things the one way and the way everybody else is doing it. Yes, you can hire a dozen cheap programmers, but one good programmer could do the same job if he or she knew how to write good code. Um, so I'm much more a libraries guy than a framework guy. I worry about overuse of framework. It allows you to do things very quickly, and then you run out of steam. You use. I mean, remember XML? You could write things fast, but it's not type safe. It's error prone like anything, and it is so slow. JSON is better, but it still has its problems.
And how has the rise of open source development impacted C++?
Oh, I think it was essential. Um, C++ did not start as a commercial product. Um, I think open source hadn't quite been invented yet, and it certainly wasn't very popular. And um, I got Bell Labs to sell the implementation, complete with source code and libraries, for $75. $75 was the cost of writing the Mac tape and mailing it. Soon after that, we got the internet, so you could actually ship it over the web. But C++ is so old that that wasn't an obvious thing to do. The average university department needed a Mac tape to get going, even though it wasn't uh, a big program.
And how do you see
One more thing. Uh, so that was the distribution, but discussing things on chat groups and mailing lists was very important for spreading the ideas, and it still is.
and how do you see C++ contributing to the development of AI and machine learning in general?
Now, I am not an AI LLM expert, and I think I shouldn't answer this question because one of the dangers of being reasonably well known is that people think you're an expert in things that you aren't, and they ask you questions, and you're supposed to have insights that you don't. So I think C++ has made one of the major contributions to LLM through TensorFlow. TensorFlow is a C++ program. It has a Python layer to make it easier to use for people who don't really understand type systems. And so it all started with C++. And I'll leave it at that. Experts can have better opinions than I have on that.
Right. And how can we define success in the context of programming language? So, what makes programming language a successful one?
Well, as I said before, the applications. I measure the quality of a programming language by the applications that it's used for. If you can build good things in an affordable way, it's good. I don't measure it in terms of how clever examples you can do in a two-column academic paper format. Uh, Sometimes you yeah, it's I'm far less interested in individual language features than what you can do in the community that uses a language. And by the way, no major system was ever written in a single language. I started out with C++ and I needed reuse. It was very fashionable reuse at the time. So what is there to reuse? C, Fortran, assembler, shell. And so it's C++ grew up in a multilingual environment very deliberately. So you could call out from C++ and you could call into C++. Quite often, when people build a language, they want that language to use other uh, languages, but the other languages shouldn't have the benefit of using things written in that language. They try to build a one-way path. That never was the idea with C++.
Right. And how do you see the relationship between hardware evolution and programming languages in the future?
Um, that's a hard question. I came out of sort of microprogramming and very close to the hardware. I mean, this is the kind of code you write when assembler is too high level. And so I think to write really good code, you need to understand something about your hardware. All the hardware is an abstraction. I mean, the instruction set is an abstraction over a micro kernel inside the uh, processor, which is, or it gets complicated. But similarly, so to write really good code, you have to understand your hardware, if it's performance you're interested in. And if you think, if you want to make good hardware, you have to understand software because, well, hardware is just a bunch of gravel if it isn't running some code. And one of the things that the languages are struggling with today is concurrency. The computer doesn't actually run a single thread much faster than it did 15 years ago. And so you need to handle concurrency. Um, C++ supports traditional concurrency in the standard that you can have threads and locks and things like that, and it supports it reasonably well and with a good type safety. Uh, but this is not a great way of writing parallel and concurrent software. It's the lowest level. So I think we need better models for dealing with concurrency. And yeah, we're working on that. The standards committee is going to probably introduce a generalization of asynchronous programming. It's something that's already deployed at NVIDIA and Facebook, but it's probably going to be standard. And so we'll be one major leg up compared to where we were in 2011, where we finally managed to get traditional POSIX, and the Windows, the threading supported in the type system.
Mhm. And what do you think is the next big challenge in software development world?
Probably um, getting tools, and that includes the language, that allow people to write good, reliable software easier. And I suspect that actually would imply that we had fewer developers, because it seems to me that we're heading with far too many people doing the same things and far too many people stepping on each other's toes. It reminds me of telephone switches. I used to work for a phone company, right? And there in the 20s and 30s, it was estimated that the whole US workforce would be telephone operators in a few decades. And you had to do something about it. And they invented telephone switches, automatic electronic things. And that's actually a major contribution to both software and hardware. And we now have very few telephone operators. We will not get to very few developers, but I think we probably has to aim at fewer, and that means higher level tools, better education. I know professors always says we need better education, but I spent almost 2/3 of my career in industry, so it's not just the standard reflexive answer.
Do you see programming as contributing to a larger human story of, let's say, understanding the world around us or the universe or something like that?
Oh, of course. Look, science is the way we understand the universe. And I don't know any field of science, as a matter of fact, I don't know any field of technology that isn't heavily influenced by computers and software. And so I feel I've done my tiny little bit to help in those areas by giving tools to people who build spaceships and people who did CERN for high energy physics. And, that is understanding the universe. Then there's other ways of understanding, like novels and history and things like that. And there's a lot of computing in there. People don't usually write their novels by hand anymore, and historians do major research using gadgets that wasn't available before. I mean, they're finding ancient cities through ground penetrating radar, which is computerized. And then all of them, there's medicine, of course. We, we're living longer and better, partly because of technology. Now, this is a very positive view. Obviously, there's misuses also, and they're major. But, that makes me uncomfortable. But when you build a tool, you have no control over who uses it and for what.
And one philosophical question: what have you learned from programming about life in general?
My first thought is no, I didn't. I learned a lot for talking to people developing systems. That is, I learned something about what can be built, how you can build it, how you interact with different people, how you can present data, how you can learn things and such. But it's not programming as such. It is from people who use programming.
How do you see basically the fact that you created something that is used by millions?
Yeah, I mean, it's all over the place. I mean, the computer here, a lot of it is C++. Our phones, what fraction of the Earth's population has cell phones? It's a very large percentage. There's very little telecommunication that isn't C++. So your TV, oh yeah, the TV itself is probably C++ somewhere. No real system is just one language. I said that before, and it's worth emphasizing. But basically, if you drive a car, if you fly, if you talk on the telephone, if you watch your television. Um, Probably I know that some of the scheduling of oceanic traffic and some of the scheduling of trains and such are C++. So if you want to eat, you probably depend on it somehow. It's somewhat scary actually, but anyway, it's all over the place.
Right. And my final question, so if you had to summarize your life philosophy in just one sentence, what would it be?
That's hard. Well, it was a good run while it lasted.
Wonderful. So, Professor Stroustrup, I would like to thank you very much for your time. This was truly an amazing conversation, and I'm sure that our audience will like it very much.
Okay, thank you very much.